Welcome to our project on energy infrastructure. This is our main project. Our group name is SMS Renewables, and it includes Andrea Grigore, Ben Whelan, Fionn Murray, and myself, Linda Riley. The first part we're speaking about is current infrastructure demand. Uh, Ireland's energy demand is projected to increase by 43% over the next decade, according to the 10-year Generation Capacity Statement 2023 to 2032 by EirGrid and Sony, which is Northern Ireland's transmission network. A report examining the balance between electricity supply and demand, identifying capacity deficits and proposing short and long-term mitigation measures. Data centers and other large energy users are key drivers of rising demand, predicted to account for 30% of electricity usage by 2032. A 2021 directive by the CRU mandates new data centers generate sufficient electricity on site to meet or exceed their demand if connection agreements are not already in place. Ireland's total energy demand in 2023 was 148.8 terawatt hours, supplied by a mix of imported and indigenous production, with gas as the primary energy source and growing contributions from wind and solar. The Climate Action Plan aims for an 80% renewable electricity system by 2030, targeting at least 5 gigawatts from offshore wind projects, with 2 gigawatts extra to be in production. The network. Ireland's electricity infrastructure consists of the transmission network managed by EirGrid and the distribution network operated by ESB networks under EirGrid's direction. EirGrid is responsible for planning, managing, and developing the transmission network, including operating Ireland's offshore grid, while networks finances, builds, and maintains the distribution network. The grid requires significant upgrades to accommodate predicted renewable energy levels outlined in CAP24, the Climate Action Plan, necessitating a more robust and flexible system to integrate wind and solar power effectively. Renewable energy integration presents technical challenges as it operates at different frequencies and often originates in remote locations, requiring conversion and enhanced grid capacity for distribution. Ireland's energy systems use advanced tools like predictive analytics and condition monitoring to improve maintenance and management. Preemptive maintenance relies on real-time data to predict and prevent failures, increasing reliability, reducing downtime, and improving efficiency. EirGrid and Sony's 2023 roadmap, Shaping Our Electricity Future, version 1.1, outlines a plan-led approach with updates reflecting the target of 80% renewable electricity by 2030 and the 5-year carbon budgets introduced in 2022. Infrastructure improvement projects in the roadmap include optimizing existing capacity using technologies like dynamic power flow controllers, creating renewable energy hubs, and building additional infrastructure. The roadmap trials increased system non-synchronous penetration, SNSP, up to 95% at rate of change of frequency, ROCOF, to 1 hertz per second, key to meeting Ireland's renewable energy goals. Decommissioning plans for wind farms may involve extending turbine life, repowering sites with updated models, or fully decommissioning. Environmental considerations and evolving recycling technologies aim to minimize waste and ecological impact during these processes. Near future schemes that are coming. Ireland's energy infrastructure is undergoing a transformation to transition from imported fossil fuels to a sustainable, indigenous, and carbon neutral system aligned with the Climate Action Plan. The Offshore Renewable Electricity Support Scheme, ORES-1, launched in May 2023, supported renewable projects with 20-year contracts, promoting investment and community participation. ORES-1 awarded contracts for 4 offshore wind projects with a combined capacity of 3.1 gigawatts, including Codling Wind Farm, Dublin Array, North Irish Sea Array, and Skerja Rocks. Codling Wind Park, located off the Wicklow coast, is expected to deliver 1.3 gigawatts and power up to 1 million homes, with completion targets between 2025 and 2030. Dublin Array on the Kish and Bray Banks off Dublin and Wicklow will provide 824 megawatts, supplying electricity to approximately 770,000 homes. North Irish Sea Array off County Louth will generate 500 megawatts to power 500,000 homes, with planning approval expected by the end of 2024. Skerja Rocks near Connemara is predicted to generate 450 megawatts for over 350,000 homes, but faces opposition due to its proximity to conservation area and nearby communities. The challenges. Port infrastructure is critical for offshore wind projects, with Belfast being the only port currently equipped for turbine assembly. Other ports like Rosslare and Foynes are planning upgrades. ORA's two auctions in 2025 will focus on plan-led projects off Waterford and Wexford coasts, targeting 2 to 2.5 gigawatts of capacity from sites such as Thundua and Lebanon. The shift to a plan-led approach involves EirGrid developing grid connections for offshore sites, including substations, landfall locations, and transmission systems. Interconnection projects are vital for energy export and import, including the North-South Interconnector, due by 2026, and Green Link between Wexford and Wales, operational by 2025. The Celtic Interconnector connecting Cork to France will be operational by 2027, with plans for further interconnections to Spain, Belgium, and the Netherlands under the National Policy Statement. Multi-purpose interconnectors are being explored to integrate offshore generation with international energy markets, enhancing grid resilience and export potential. Challenges include community opposition to renewable projects, insufficient port facilities, and grid capacity limitations, all requiring strategic planning and upgrades. Ireland's focus on interconnections and offshore renewable energy positions the country as a potential global leader in sustainable energy, supporting UK and European market integration.
So for infrastructural requirements, energy security, maturity, and future proofing and decommissioning. We have Ireland's electricity infrastructure and energy security. So for transmission and distribution, then EirGrid manages the high voltage transmission network, ensuring efficient electricity flow from generators to substations, while the ESB networks handle the lower voltage distribution to homes and businesses. Both entities are key to maintaining a reliable power supply across Ireland, and with the increase in renewable energy capacity ongoing, upgrades aim to integrate sources like wind and solar while enhancing grid stability through advanced technologies like dynamic voltage control. Then the Celtic Interconnector. This major project connects Ireland's grid to France, allowing for electricity trading between countries, and it strengthens energy security by diversifying supply sources and provides access to broader European energy markets, which helps mitigate risks associated with domestic supply variability. So the DS3 program and generating capacity statement. So EirGrid's delivering a secure, sustainable electricity system initiative focuses on operating the grid securely with high levels of renewable energy. It addresses the technical challenges of renewable integration by developing technologies like enhanced frequency response, system protection upgrades, and fast-acting reserves such as battery storage. The generating capacity statement outlines future electricity supply and demand, projecting a 2 to 4% annual demand growth driven by data centers and electrification of transport and heating. It highlights the need for significant renewable expansion, including large-scale wind and solar projects, to meet the Climate Action Plan's goals of 80% renewable energy by 2030. For renewable energy and grid development, so onshore and offshore wind energy are central to Ireland's renewable strategy, with projects like the Arklow Bank Wind Park Phase 2 and new developments in the Celtic Sea set to increase capacity. Solar energy is also expanding, supported by government grants for rooftop systems and large-scale solar farms, contributing to a more diversified and resilient energy mix. So developing the grid then, the network development portfolio focuses on expanding the grid to accommodate increasing renewable energy, and this includes upgrading transmission lines, building new substations, and integrating advanced monitoring systems. Interconnectors like the one to France are key for accessing Europe's markets and exporting surplus renewable energy, enhancing grid reliability and security. For energy storage and future proofing, technologies like battery energy storage systems and pumped hydro storage like Turlock Hill play a critical role in balancing supply and demand. So the BESS has helped manage short-term fluctuations, while the pumped hydro offers long duration storage by using excess energy to pump water up, which can later generate electricity when needed. And for future proofing, to ensure long-term infrastructure viability, modular designs allow for easier upgrades and adaptations as technology evolves. Climate resilience is crucial, with infrastructure designed to withstand extreme weather events and sea level rise. Predictive maintenance using digital twins and IoT sensors, ensuring early detection of issues, reducing downtime and costs. Sustainable decommissioning focuses on recycling materials and repurposing old sites for renewable projects, minimizing environmental impact and supporting the transition to a low carbon economy.
So Ireland's energy targets then Ireland has ambitious targets to meet. They're set up by EU regulations. Ireland is expected to reduce its greenhouse gas emissions by 55% compared to 1990 levels by 2030 and be completely carbon neutral by at least 2050. Um, the policy commitments laid out in the Climate Action Plan 2022 and 2023 include achieving 80% electricity demand coming from renewable sources, 5.7 terawatt hours of biomethane used across heat sector, and district heating growth of 2.7 terawatt hours. Key targets set out from the Climate Action Plan 2024 are 9 gigawatts of onshore wind and at least 5 gigawatts of offshore wind, and 9 gigawatts of solar by 2030. Um, it is not only the government that sets the targets, there's organizations that set out their own targets as well, like the EirGrid and the ESB. Um, EirGrid has four scenarios that it sees to meet their targets. The first would be the self-sustaining target, or self-sustaining path, which is a reduction of fossil fuels very quickly and a vast electrification of all sectors that sees net zero achieved by 2040. The offshore opportunity sees a similar speed and reduction of fossil fuels, but the electrification coming through offshore wind. This achieves net zero by 2040 as well. And this path sees Ireland becoming a large exporter of electricity because the offshore capacity is much higher than Ireland's demand would end up being. Um, the constrained growth path has a very slow reduction in fossil fuels and a very slow electrification of sectors. Um, this is the worst net zero one, net zero by 2050, and is nearly the opposite to offshore opportunity. And would see Ireland becoming a large importer of electricity through interconnectors and such. Um, the gas evolution then sees a significant renewable generation for both electricity and electrolysis for the production of green hydrogen for e-fuels and export. That would have a net zero by 2045. This is similar to offshore opportunity and sees Ireland becoming a large exporter of energy, but not through interconnectors, more through e-fuels and green hydrogen. The ESB also has its own targets that it set out. The ESB is committed to net zero by 2040, committing to a five-fold increase in renewable generation and reducing carbon intensity by two-thirds by 2030.
Ireland's energy infrastructure and transmission. The infrastructure for energy transmission and distribution in Ireland is managed by EirGrid and ESB networks, while EirGrid designs the improvement in electricity transmission. ESB networks services and administrates the distribution of electricity, being responsible for further transmitting electricity to the distributor. EirGrid is controlling the nation's electricity grid while focusing on stability and reliability. While complying with the government's climate plan of action, EirGrid's plan sums up the important actions required for achieving a future where up to 70% electricity is generating from renewable sources. ESB network is committed to permanently providing safe new plans for a stronger and more reliable network. The integration of different technologies, such as dynamic line rating, helps reducing overload on power line and increase effectiveness while generating lower costs.
Right. So, renewable generation. Wind is the major um, renewable energy source for Ireland. Of all the electricity produced, 34% came from wind, 2.2% from hydroelectric, and 1.9% from solar PV, and 1.9% from biomass. Currently, Owenini wind farm is the largest wind farm in the country, with an installed capacity of 192 megawatts and is produced through 60 turbines that are spaced out over 2,400 hectares. To meet the targets for onshore wind of 9 gigawatts by 2030, Ireland will need to manufacture another 18 farms of similar size to Owenini. For offshore wind is on a very different path to onshore wind. The only offshore wind farm in operation today is Arklow Bank in the Irish Sea, is approximately 10 kilometers offshore. It's a 25 megawatt wind farm consisting of seven 3.5 megawatt turbines. These turbines are monopile driven, um, and they rest in a shallow sandbank. If this wind farm is to be the standard wind farm built in Ireland over the next 5 years to reach the ambitious target of 5 gigawatts of offshore, 200 wind farms with this capacity of Arklow. 200 wind farms of the size of Arklow Bank would have to be built, but they are much larger wind turbines built today than you see in Arklow Bank. Um, Solar and hydro, the other two large producers of renewables. Solar is the fastest growing renewable energy source in Ireland and shows great potential in the future. In 2023, solar PV was running at a capacity of 0.72 gigawatts in Ireland, up from 0.19 gigawatts the year before. The largest solar farm in Ireland is in Gallenstown Solar Farm in County Meath. It's a 500-acre farm with a capacity of 198 megawatts. For hydroelectric, it doesn't show nearly the same growth as solar. It's fairly static. Ardnacrusha will continue to be the largest hydroelectric power station in the country, outputting a consistent 86 megawatts of power that's day and night all the time, rain, sun, or shine. Turlock Hill is the only hydroelectric storage, was more of a storage facility for the country that's capable of storing 292 megawatts.
Offshore wind generation. Offshore wind generation converts the kinetic energy of wind over open water into electricity, benefiting from higher and more consistent wind speeds compared to onshore systems. Ireland's expansive maritime territory and strong wind resources make it a prime location for offshore wind energy development, with several projects already in planning or execution. Offshore wind systems are classified into fixed bottom and floating turbines, each suited to different water depths and environmental conditions. Fixed bottom turbines such as monopiles, jackets, and gravity based structures are anchored to the seabed and used in shallow waters up to 50 metres deep, like in the proposed Codling Wind Park project. Codling Wind Park, located in the Irish Sea, is one of Ireland's largest planned projects, aiming to generate up to 1.5 gigawatts using fixed bottom structures. Floating turbines anchored with mooring lines are designed for deeper waters and are suitable for Ireland's west coast, where robust wind speeds and deep waters offer significant potential. Projects like the Western Star floating wind farm are exploring these opportunities, marking advancements in offshore wind technology. Site selection for offshore wind farms considers environmental, logistical, and technical factors, focusing on areas with strong wind resources, shallow waters, and proximity to population centres. The south and east coasts of Ireland, with shallower waters and grid accessibility, are hubs for projects like Oriel Wind Farm off County Louth and proposed ORIS 2 projects such as Lee Bawn and Thonnua. Offshore wind infrastructure requires offshore substations, subsea cables, and dedicated port facilities for construction, assembly, and maintenance activities. Investments in port facilities such as Rosslare Europort indicate Ireland's readiness to support large-scale offshore wind development. Environmental sustainability is key for Irish offshore wind projects, with the rigorous environmental impact assessments and stakeholder consultations guiding project planning. Thonnua, a proposed offshore wind farm off County Waterford, incorporates spatial flexibility to minimise environmental impacts while maximising efficiency. The new Planning and Development Act 2024 makes this flexibility possible. Offshore wind is central to Ireland's renewable energy goals, reducing carbon emissions and enhancing energy security, with projects like Codling Wind Park, Oriel Wind Farm, and Western Star leading the way. Continued investments in advanced technology, infrastructure development, and environmental assessments are critical for Ireland to unlock the full potential of its offshore wind resources.
Offshore investigation specific region. Located on the coast of Ireland facing the Celtic Sea, the Blackwater region is convenient for offshore wind farms construction due to its significant and reliable resources of wind. Before starting the development of a wind farm in this area, several evaluations were conducted to investigate the marine species, the seabed properties, and the weather conditions. The Blackwater offshore wind farm presents great potential for producing considerable amounts of energy given its location and technology. Considering the information from the wind atlas provided by CEAI, the Blackwater area experiences an average wind intensity between 8.9 and 10.1 meter per second, which makes it suitable for generating significant amounts of wind energy. To achieve a detailed overview of the marine area in the Blackwater region, it is important to consider the SCD map plan. The plan outlines 4 priority areas for offshore wind projects, construction being accelerated here. These areas contribute to the country's renewable energy development goals. Based on the criteria presented by the SCD map plan, the development of the Blackwater offshore projects complies with the European standards for renewable energy farms, avoiding restricted areas where the development of the offshore projects can proceed due to the environmental constraints.
So for offshore to onshore infrastructure, we've got offshore wind farm layouts. So the turbines usually arranged in rows and columns just to optimize energy capture. Turbine spacing then is usually 6 to 10 rotor diameters apart or more, and this reduces wake effects or turbulent air and enhances array efficiency. So for design considerations, the factors like wind patterns, water depth, and seabed characteristics are key to layout design. For offshore substations, then their function is that substation converts generated electricity to higher voltage for transmission via subsea cables, and they're positioned near the wind farms on floating platforms or fixed structures depending on the water depth. So the role of these then is that it consolidates power from turbines and stabilizes it for efficient onshore transmission. For ground evaluation from the likes of Infomar and GSI. So the Infomar provides high-resolution mapping of Ireland's marine environment, including bathymetry, sediment composition, and underwater features. So this helps to determine suitable locations for wind farm arrays and cable routes, ensuring stability. So soft sediments may require additional anchoring or protective layers for cabling. For GSI then, so this supplies more of the geological data on the seabed geology, including rock formations, fault lines, and other hazards. So this will guide engineers in planning offshore cable burial, anchoring systems, and subsea infrastructure. The impact in this sense that low bearing capacity of the seabed influences the design of offshore substations and installation methods. For offshore cable installation techniques, so the cable types usually high voltage alternating current or high voltage direct current. So it's usually the HVAC for shorter distances, and HVDC is preferred for long distances, the likes of above 60 kilometers due to its efficiency. They're usually multi-layer cables, including a conductor, insulation, armoring, and protective coating for harsh marine conditions. For cable installation techniques, then with ploughing, which is cable buried underneath seabed to protect from external factors like fishing nets or anchors. Trenching, which is where the cable is placed on a trench and covered with seabed material. So this can be used for deeper burial in soft sediments. And surface laying, where the cable be laid on the seabed and covered with protective rock or concrete mat in rocky or shallower areas. Connecting and anchoring. So for anchoring, we drag embankment or gravity-based anchors used for stability in deeper waters. And for connection, it'd be sealed connectors and transition joints that secure cables to the offshore substations. For the connection to onshore then, so the onshore substations are for step-down high voltage power from offshore substations to a voltage suitable for integration with the onshore grid. And they're typically located near the coast where the subsea cables make landfall. And their role then is to distribute power to consumers across the country and into the national grid. So the techniques for offshore to onshore connection, the offshore portion is the cable laying vessels used for subsea cable installation, and the onshore portion then would be trenching or ploughing techniques used for burying the cables. So planning considerations is careful design of the shore connection point to protect the cables from damage and minimize environmental impact.
So discussion of enabling works for cable lay connection. A point picked for the cable lay was just east of Salt Mills here in County Wexford. You see it on the map here. A basic plan of the area was made up in the GeoHide map viewer, where the orange box is a substation and the solid red line shows the cable flowing out to an energy hub such as Money Point and the likes. And the blue line in the circle indicate an alternate route for future works such as batteries or distribution network. The purple highlighted dashed line shows the location that the cofferdam will be used to bring the cable ashore. The cofferdam itself, the depths of the wall of the cofferdam are embedded, and that depends on the angle of internal shear strength and the bulk density of the material that it's being embedded into. The angle of internal shear strength gives the coefficients of active and passive pressures of the material. For regulations, the depth of the trench of the cofferdam was set to 3 meters because the water depth can go up in 2.4 meters. These are the values that we need to start to calculate a safe depth to embed the walls of the cofferdam during construction. So our next slide here is a basic diagram here of one of the walls of the cofferdam. It's a net force diagram that shows the sum of the active and passive forces acting on the walls in the black lines that go from left to right, then right to left, and left to right again. The distance down, the first distance you have to calculate is the distance down to point A, which is the point of there's no net pressure. The pressure pushing down from the sediment on one side is equal to the sediment from the other side. This was found by, you equate these pressures on either side of the wall, and it was found to be 0.37 meters. You use this now to equate the forces. All the forces there with the black arrows sum to 0. Firstly, to do this, they have to find the stresses through the red lines PP1, PP2, and PP3. PP1 and PP3 were found by calculating the stress from one edge of the line and subtracting from the stress to the other edge. PP2 can be calculated by subtracting the pressure coefficients. That gets you this angle of the force line itself. Multiplying this by the bulk density and the height of the matter under point A where there is no net pressure. These are all the bases of the force triangles that have been calculated. You get the actual forces of these triangles, you get the area of the triangles themselves. So the yellow, you can't really see it there, but the two top triangles, black triangles there where PAs are labeled 1 and 2. So that there was the area of those two triangles give you the area of PA, and then you find the forces of ZC, C dash, and FAB, C dash. This gives you a value for Z, which is seen on the right-hand side here, which we'd hold for later on because we need to find another equation to find a value for Y. This we use the moment of a force equations, where the moments of a force we calculated all the moments added together equate to 0 around an arbitrary point. Point B at the base of the wall was chosen, and we multiplying each force by the length of its lever arm from this point, we calculate the moments. Each force in the triangle acts through the centroid of their triangles, which is a third of the way up from the base. So that gives us the following equation that you see here. A bit complicated and hard to put into a PowerPoint slide, but once you add this up, you can sub the Z into it and equate that all to get your Y's. The Y then is added to the distance A dash here from A to the surface, and with a 30% margin for safety, it gave a value of 3.95 meters for the depth of the walls of the cofferdam. Now foundation design types. For offshore wind, as Linda said, there's two types, basically fixed and floating. Since we're looking at the Blackwater region where the depths are over 50 meters, we concentrated here on floating foundations. Floating wind turbines are typically designed one of 3 ways, either semi-submersible platform, tension leg platform, and spar. Both semi-submersible and tension leg platforms operate at depths approximately 60 meters, while spar can operate at depths up to 100 meters. All the turbines are assembled the same way. The turbine is assembled in a protected waterway from harsh environmental conditions, and then the turbine is towed out to operating location where it's tied to the seabed. The equations that govern the foundation design, basically the buoyancy and the weight forces have to balance from the air within the floating platform or spar. The tension in the cables and the anchor points must hold up the forces applied from the wind and the waves. The forces from the wind can be calculated with the following formula, where C is a shape coefficient, basically a measure of the smoothness of an object. The lower the shape coefficient, the smoother the object is. Q is the wind pressure, and S is the projected area of the object. While alpha is the angle between the wind exposed and the axis of the object itself. The force from the waves on a semi-submergible object at a particular time can be calculated by the following equation here. Here, v is the wave velocity and v dot is its acceleration. A is the cross-sectional area, while d is the cross-sectional diameter. Rho is the fluid density of the water. CD is the drag coefficient and CA is the added mass coefficient. These are similar to the shape coefficient, but they allow for the buoyancy of the object, and it has to be split in two as the object is semi-submersible. Some of it is under the water and has to be treated differently to that over the water. Tying these to the ground itself is the anchor. There are three types of anchor, which is gravity, which is just a large mass, usually of concrete, that is just sitting on the seabed and something is tied to it. Piles are like the large just mini versions of the monopiles driven into the ground, and plate anchors, which is like the ones in this diagram here. And as it shows that plate type anchors perform the best and are the easiest to grow in size as the wind turbines grow. These anchors work like a typical ship anchor. They're dragged through the seabed, and when they're pulled along the sand sediment, the anchor keeps them in place then when they're pulled below the surface. This works very well in the sand and silty seabed around the Blackwater region.
Construction requirements on infrastructure for a buried cable. High voltage DC cables offer essential benefits. They ensure the connection of circuits that do not operate simultaneously, deliver great amounts of energy across extended distances, and experience reduced losses. A 500 megawatts HVDC cable requires infrastructure designed to handle high voltage DC energy efficiently while being compatible with both the offshore supply chain systems and the onshore delivery technologies. To ensure a successful integration process, the infrastructure of a high voltage DC system needs to include conversion stations on both of the offshore platform and the onshore grid. The materials typically used for developing a cable for HVDC systems are copper and aluminum due to their high conductivity power and insignificant amounts of losses. Develop a suitable underground cable route. The image represents the proposed underground cable between Blackwater and Money Point that was designed using the ArcGIS tool, consulting Environmental Protection Agency data, which offers detailed information about the environment. The approximate location for the preferred corridor for emerging the onshore cable landing from Blackwater was carefully chosen based on map data provided by national parks and wildlife service, avoiding any special areas of conservation. When creating the cable route, the Office of Public Works guidance on controlling the risks for flooding was followed. The high-risk indicated areas were avoided to secure a safe and effective route development. Given that the cable route extends over 250 kilometers, it inevitably crosses a few of the major rivers and waterways in Ireland. To reduce the negative impact on the seabed surface situated above the drilling area, horizontal directional drilling is required, being a method that ensures natural recovery for the area after the installation processes.
Relevant legislation on route selection and infrastructure. Ireland's energy infrastructure development operates under a complex legislative framework, balancing national energy objectives, environmental sustainability, and stakeholder rights. The framework integrates EU directives and national policies to ensure compliance with international obligations and Ireland's climate neutrality goals. The Maritime Area Planning Act 2021, MAP Act, provides a foundation for sustainable maritime development, creating the Maritime Area Regulatory Authority, MARA, to oversee planning and licensing within Ireland's maritime zone. The MAP Act aligns offshore and onshore development through the National Marine Planning Framework, NMPF, enabling coherent decision-making across jurisdictions. Offshore energy projects are regulated by the Foreshore Act 1933, requiring foreshore leases or licenses for developments impacting the seabed or coastal waters with strict environmental compliance. Onshore energy infrastructure is governed by the Planning and Development Act 2000, with large-scale projects falling under the Strategic Infrastructure Development (SID) process for streamlined decision-making. The updated Planning and Development Act 2024 aims to reduce planning application timelines, deter planning abuse, and provide design flexibility as part of the changes, which will help to accelerate renewable energy projects. Legal considerations for land acquisition are addressed by the Electricity Supply Act 1927 and Gas Act 1976, granting semi-state bodies compulsory purchase powers with fair compensation and transparency. Transportation of large components such as wind turbine blades is governed by the Roads Act 1993, requiring permits and route planning to minimize disruptions during construction phases. The Road Management Office, established in 2014, standardizes licensing processes for road openings and excavations, an essential part of all energy infrastructure projects and grid upgrades. Relevant legislation on route selection and infrastructure. Environmental compliance is mandatory under laws such as the Environmental Protection Agency Act 1992, Birds and Natural Habitats Regulations 2011, and Climate Action and Low Carbon Development Act 2021. These laws ensure that energy projects align with Ireland's climate goals while safeguarding biodiversity, water quality, and community well-being. The emphasis on all of the latest government legislation and updates is on a plan-led approach to all developments. Environmental assessments, such as appropriate assessments and strategic environmental assessments, are incorporated into the development of these plans. Compulsory public consultations, environmental impact assessments, are required for significant projects to address community concerns and mitigate environmental impacts. Coordination with transportation authorities ensures energy projects integrate with existing and planned networks, minimizing logistical challenges. The legislative framework underpins responsible infrastructure development, with updated laws expected to expedite construction and support Ireland's renewable energy and emissions reduction targets.
So, future-proofing and maintenance. Regular inspection is needed on all aspects of offshore wind farms because they're constructed in steel. They're subject to corrosion and wearing of protective coatings. As floating turbines ride on the waves, they can be shifted easily. They can be shifted, especially if the frequency of the waves matches the fundamental modes of the mooring cables. This means that mooring cables and anchors have to be inspected regularly also. To help maintenance in the future, long-term projections of weather forces can experienced by wind turbines could be modeled using faster computing or AI. Climate change offers another set of challenges to offshore wind. Research has shown that climate change might actually decrease offshore wind capacity, but not enough for it to be considered a not viable renewable energy source. Increased volatility of weather may pose a problem for turbines. A way to combat this would be to add pitch and yaw motors to combat the sway that a turbine would experience during heavy weather. Also, individual pitch control blades be a viable option to reduce stress. When the pitch of each blade is controlled independently, it is shown to reduce the load on the blades by up to 20%. There are many ideas for future-proofing turbines, so they can provide electricity to help meet other long-term climate targets. Adding green hydrogen production through electrolysis at the base of the turbines could help produce in the production of e-fuels, decarbonize the transport industry as well as the electricity production industry. Cable bays could also be equipped with large batteries with grid scale storage, as offshore wind generation surpasses the grid's demand.
For roadworks then. So the strength, condition, and design of Irish roads. So for the strength of Irish roads, it's assessed through deflection testing, so falling weight deflectometer, and visual condition surveys. So it's designed to handle diverse traffic loads, heavy agricultural machinery on rural roads, and then urban traffic on developed routes. So traffic classification system by TII evaluates the expected traffic volume and weight distribution on these roads. So the design of them then adheres to Transport Infrastructure Ireland standards, primarily flexible pavement systems for load distribution and durability, and they follow the design manual for roads and bridges. So this considers traffic loading, climate, and subgrade strength. So multi-layer design, subgrade, subbase, a base, and surface layer for strength and longevity. For the subgrade then, it's usually a natural soil foundation. It's often clay, sand, or rock, and it supports the road structure and traffic loads. So considerations and that bearing capacity is assessed pre-construction, and soil stabilization is used if the subgrade is weak. For the subbase layer, it's made of crushed stone, gravel, or recycled aggregates, and its function is providing drainage and prevents water accumulation. So it stabilizes layers above and prevents the frost heave as well. For the base layer, it's constructed from granular materials like crushed limestone or granite, and its function then is to add strength and distributes traffic weight evenly across the surface. The thickness is tailored to the traffic volume and the subgrade capacity. For the surface course, then, which is the asphalt layer, it's composed of a hot mix of asphalt, including bitumen, aggregates, and additives. And its function then is to ensure a smooth, durable, and skid-resistant surface. So this is designed for Ireland's wet climate and high traffic wear. For road opening and reinstatement, so the purpose of road opening then would be closed for installing utilities like the power cables for the offshore wind energy transmission. The guidelines then are to follow the NRA road opening and reinstatement guidelines. Key steps are planning and permissions, so obtaining a road opening license and that complies safety environmental regulations. Excavation, so creating a clean trench with saw cutting or cold milling, which requires depth and protection for cables. Health and safety then, so implement safety barriers, signage, and traffic management plans to protect workers and minimize any disruption. Reinstatement of roads, so the objective then is to restore the road to its original condition. The key steps are layer by layer replacement, so reconstructing the subbase base surface layer with proper material compaction. Surface reinstatement, so applying a final asphalt layer for a smooth level finish and matching the existing road. Quality control, which adheres to standards for compaction, smoothness, and surface quality, and issue reinstatement certificate of bone compliance. Considerations then are the bearing capacity assessed pre-construction, soil stabilization used if the subgrade is weak. So the material and function of each layer. So the installation in existing roads, they would use trenching, which is a traditional method involving road excavation and reinstatement. It uses cold milling for pavement removal and directional drilling for minimal disruption. So directional drilling is preferred for minimal surface disruption. It's used in urban and environmentally sensitive areas, and cables can be installed beneath the road without full excavation. So installation in new roads, so the design phase integration, cables will be placed in ducts or tunnels before final asphalt layer, reducing future excavation and ensures easy maintenance access. Protection options, so the cables can be directly buried in ducts or encased in concrete for extra safety. And then the cable types would be the high voltage, alternating current or direct current, depending on the distance between the offshore wind farm and the land facilities.
Energy storage. Given Ireland's considerable reliance on wind power and its efforts to reduce the nation's carbon footprint, a 2022 report determined that most of the sustainable electricity was supplied by wind farms, contributing to with more than 85% of the electricity. The nation's initiatives to minimize the emissions in the energy sector and to decrease pollutant levels through renewable energy can be supported by introducing additional storage systems. The system will enhance the effectiveness and security of renewable energy by making up for the energy losses and supply variations impacted by different climatic conditions. Storage systems based on battery or pumped hydroelectric energy are some of the systems suitable for Ireland's energy infrastructure.
The energy infrastructure cluster, which shows money point. So location and site selection. So strategic location on Shannon Estuary with deep water port access for offshore wind turbines, proximity to existing energy infrastructure and skilled workforce, and minimizes ecological distribution and leverages high wind potential. So enabling works for this then will be to decommission the coal infrastructure and environmental remediation, coastal protection and soil stabilization for long-term resilience, and dredging to accommodate heavy lifted vessels. So site layout and structures and facilities for wind turbine assembly, hydrogen production, and energy storage. So for offshore wind integration, it would be a gigawatt scale offshore wind capacity with advanced floating turbine technologies. Floating platforms would be ideal for Shannon Estuary seabed and its water depths, and this will align with the EU goal for 300 gigawatt offshore wind capacity by 2050 for the country. So our green hydrogen production on the Money Point site as well. So renewable powered PEM electrolyzers for hydrogen production at high scale and supports decarbonisation of transport, heating and industry, and the potential for Ireland to become a hydrogen export hub, which is similar and inspired by the port of Rotterdam, what they're doing at the moment. For energy storage then, with vanadium redox flow batteries for scalable and durable storage, compressed air energy storage for long duration needs, and these are inspired by the Hornsdale Power Reserve success in grid stabilization. So grid enhancements, modernized grid with dynamic load balancing and real-time monitoring, HVDC lines for efficient energy export and reduced losses, and smart grid integration inspired by the North Sea Wind Power Hub practices as well. So final evaluation of the Money Point site is this energy hub then. So the infrastructure readiness, so timely enabling works, utility upgrades and grid installations are critical. Risk of delays as seen in the Cape Wind project highlight importance of phased implementation for planning and prioritise critical path items to mitigate regulatory and logistical challenges. So technology integration, so flexible modular technologies ensure scalable and future readiness. Lessons from the Anholt offshore wind farm on modular design for efficient operations should be looked at for these considerations. Seamless compatibility between turbines, hydrogen facilities and storage systems will be essential. Economic viability, so high upfront cost balanced by long-term benefits, job creation, energy security and hydrogen exports. The policy support and incentives are crucial, as demonstrated by Germany's Energiewende initiative. So continuous cost benefit analysis to align with climate and economic goals. For a strategic outlook then, so the bold vision, leveraging location, technology and infrastructure to lead renewable energy. This success will depend on if we can overcome key challenges with strategic planning and innovation, but it will be a blueprint for future initiatives reinforcing Ireland's climate leadership. In conclusion then, so this project highlights the critical role of renewable energy infrastructure in meeting Ireland's climate goals. The integration of offshore wind between Blackwater and Money Point is pivotal for boosting renewable output, ensuring grid stability and enhancing energy security. Targeted investments and strong policies can drive this transition, while addressing environmental social factors is key for sustainable development. By fostering innovation and stakeholder engagement, Ireland can lead in global sustainable energy practices, securing a resilient and economically viable future.
Thank you.